forza, no? Perché se si devono guardare, non possono essere uguali. Sì, ma io mi immagino che i 3 radiation point a riferimento del satellite sono montati nello stesso punto. Però i satelliti sono stop, sì, ma i satelliti tra di loro sono girati, perché sennò non si possono guardare. faces are not so good until I've seen people a few times.
When you turn it on, you get a little battery indicator. This one's for me.
It's interesting because
You get a little battery indicator.
so you were originally
Right.
yeah, it's interesting with the Italian names. Like Daniele, sometimes it can be a female name, right? So sometimes it's like confusing.
Okay.
Test it. Oh, I heard you very well. So it's not on yet. When you're ready, I just want you to accidentally. And then this is the clicker. And we talked about down is forward.
Okay.
Great.
Okay, great.
All right, everyone.
Yeah, turn on.
Turn it on first.
Turns out.
All right, everyone, please settle down, get your seats. The next session, we're already behind. Not doing well. Okay. So our first speaker is Daniele Vetrugno from Hanover and is going to be telling us about the LISA Pathfinder heritage here.
Okay, can you hear well? Good. So, good morning, everyone. I'm Daniele Vetrugno from the Albert Institute in Hanover. Sorry, I was used to say University of Trento for many years, so I was going to say the same. No, Albert Institute in Hanover. So today I will try to give you I have the honor to give this celebration talk about LISA Pathfinder, the 10 years since we launched LISA Pathfinder. There was, as you know, the technology demonstrator for LISA. And okay, when I first thought about this talk, actually, this is the more institutional title. I thought more about this one, LISA Pathfinder, an interesting journey from picophobia to femtomania. Yeah, probably is what happened at the beginning when some crazy scientists say to the agency, hey, guys, we want to measure differential displacement between two free falling bodies in outer space at 2.5 million kilometers with picometer accuracy. Yeah, maybe picophobia. And then we arrive to femtomania, where we are all excited and really obsessed by measuring our femtometer per second square per root hertz of residual acceleration between test masses. So I think this fit well with what could be an instrumental summary, but also a psychological one. So I just will try to drive through this journey. And this journey took quite a while, but it was worth it, and it was all done by a reason, the whole LISA. Now, this plot is only for completeness. I won't talk of that, because after 1 week of LISA, maybe you don't want to hear that. No, I'm joking. Maybe you know everything about that. And so, but the thing that I want to say is about the three pillars that enable the sensitivity to gravitational wave in LISA, just because this will bring me to talk about the motivation for LISA Pathfinder, why we did it. And so the first pillar is the fact that you have to measure with picometer accuracy this distance, so that your sensing, your readout has to be able to do this measurement. And the second one is the fact that you have to suppress the laser frequency noise. We have heard about these two in these days by Ryan, Hada, Jean-Baptiste. They are very challenging, but some way, you can test on ground many things, and some way with enough confidence you can project to what will happen when you will have long-arm interferometry. The third pillar is the quality of the free fall. And you have to be able to put the test masses, your proof mass, in a quality of free fall that reach the femtometer per second squared per root hertz. Okay? And this is important first because if there is a force attacked on the test masses, this will make the test masses move, and at that point, how you can say that it's a gravitational wave or it's some force, local force noise deducting on that. And the second thing is that this source of noise dominates your sensitivity below a few milliards. So it's an important contribution. Now, then you can ask yourself what we know about the force noise. And this, you see this amplitude spectral density in acceleration units on the y-axis as a function of the frequency. And the black one is the LISA requirement. The gray one is the LISA Pathfinder requirement. And this green one, let's say blue one, green one, is what we can measure on ground with torsion pendulum that was built in Trento. However, you see we are an order of magnitude maybe do somewhere worse. However, this is not a direct measurement. It's a measurement of the torque noise, and then from that you infer what could be force noise, but not any force produce torques. On top of that, the test mass has hollow. It's not really representative. There is not the full hardware around the spacecraft. So it doesn't help too much to give the confidence enough to trust that you can do this, the LISA one. And you can ask also what we can do from space, what we know. We have mission already that prove the acceleration noise. Yes, we have, but were these two before LISA Pathfinder, Grace and Gauche. And I want you to notice that here each big tick is one order of magnitude. So we have a huge ignorance, quote unquote, space before LISA Pathfinder. However, the force noise, we say, is local noise. It acts where the test mass is. So we can squeeze one arm. We don't need the 2.5 million kilometers to test the force noise. We squeeze that to 38 centimeters. We put the two test masses in the same spacecraft. This is the idea behind LISA Pathfinder. Test this force noise with this configuration. And this is the LISA technology package that contains, it's the core of the experiment. It contains two LISA GRS, and I put on purpose LISA GRS because the idea since the beginning was to build something that then you can bring and put on LISA. Of course, we have heard that there will be some change. However, be careful. They should be very small delta change and things that we are sure we don't introduce anything that you don't want that you don't, when you measure with LISA Pathfinder. Otherwise, the legacy will be all lost. And here in between, you have the LISA Pathfinder optical bench. This is the LISA Pathfinder because the optical bench in LISA will be different. So I will talk of the optical bench later a little bit. Let me talk about the GRS because that is the core of the test for the acceleration noise. So you have heard already from Rita the first day that there is a gold platinum, a gold platinum test mass here. It's very heavy. It's 2 kilos, 46 millimeters of H. It's very low magnetic susceptibility, such a way you don't couple with any magnetic force, any magnetic field. It's gold coated, as also it is the electrode housing, this cage that acts both as a Faraday cage, so the electrostatic stray forces outside the cage are shielded by this, and with these electrodes as a position sensor and force actuator. Then we have a source of UV light that is used to shine on this gold-coated surface and use photoelectric effect to extract electrons and moves between the tesma and the electrode housing in such a way that you can null the charge that is accumulated on the tesmas because of the cosmic rays, because this charge will couple with any stray fields, electrostatic fields, to make a force. And then we have the titanium vacuum chamber that is there to maintain a certain level of vacuum. We want order of micropascal there. And a couple of other mechanisms. One is to keep the tesmas hold when we launch. Another one to release the tesmas. And then a vent that, here you cannot see, but it's like a pipe that goes outside and is open when in orbit to pump out the residual gas to the outer space. Okay, so you put the two tesmas in the same spacecraft, what happens? There is the spacecraft. If there is a self-gravity of the spacecraft, it will pull the tesmases, and after a few seconds, they will crash on the electrode housing. The experiment ended. So you have to find a trick to cope with that, and the trick is this one, and this is the working principle is about Pathfinder. You take one tesmas, this one, tesmas one. This is really free, it is controlled, not degrees of freedom, but really freely falling along the sensitive axis, the one that joins the two tesmases. And then you have an interferometer that measures the displacement between the optical bench that is attached to the spacecraft and this tesmas. And this is the error signal to a control loop that activates some micronewton thruster that gently move the spacecraft following the tesmas, the first tesmas, without touching it. At the same time, you measure the distance between the displacement between the two tesmases with another interferometer, the differential one, and this is an error signal to this so-called suspension control loop, by which you apply electrostatic force on the second tesmas to keep the distance between the two fixed. In this way, if you do the maths, and I don't want you to do the maths, but if you do it, you get that the spacecraft, the force applied on the spacecraft is rejected, and you get this quantity, delta G, that is the magic quantity you want to measure, the really free falling quality, that is practically dominated by the commanded force. So what you command is what you want to measure. Okay. So, and when you assemble all this is the hardware, the LTP. And every experimentalist that has gone into the lab goes here, look there, and say, how the hell it can work? It's a lot of cable, complicated structure, and you have to measure very, very tiny quantity. Anyway, even if someone could be scared, the team was very confident. We can do it, the day of the launch. This is the launch date. And someone was spraying. I think San Gennaro is the patron of Naples. It worked, because at the end, we launched. And maybe I lived for a few seconds with the thrill of the launch, because an entire career of someone was here.
9, 8, 7, 6, 5, 4, 3, 2, 1, top, allumage et décollage de VV06.
Very good. Yeah, it was done. First single failure point, done. It's not the last one, unfortunately, because then we have 1 month to go in orbit. We switch on the system, and first thing, we have to decage the tesmases. This is one single shot mechanism. If it doesn't work, the mission is ended. And we have this 8 finger here that you can maybe see that apply kilonewton on the tesmas during the launch, and you have to hand over to this other finger that keep the tesma with few newton. When you do this, when you release this, also the venting duct open, the valve open, that one that is connected to the pipe that make the residual gas pump out to the other space. However, this was successful, sorry. After that, you have, as I told you, release the tesmas. So this 2 pin has to be retracted gently and simultaneously. And here you can see is a reproduction from the data. And I don't know if you can really appreciate what is happening here. What is happening is the tesmas crash on the electrode housing. Very, very difficult moment. However, the team in ESA and the scientist was really amazing. They were able to, some way, using these fingers to move the tesmas and then release safely and make the tesmas be controlled by the electrodes. Because the idea is that when you release, then you have the electrodes switched on, and they will take the control of the tesmas.
YouTube now.
They were happy. Of course, they were happy. And this is the first few hours of operation in which first so here you see on the y-axis the applied force on the test mass versus the time, and here these red lines are the different mode in which you can control the spacecraft and the test mass. So at the beginning you control in so-called accelerometer mode, so the test mass follows the spacecraft. And you can see it's a lot of noise because the thruster are noise and so on. After a while, you go in science mode, in which the test mass, the spacecraft follow the test mass, and it's much, much better. And so the operation can start. And so let me spend a few words about the operation, because I think it's important. There's also have some lesson for LISA when it will be in flight. So we had about 500 days of operation. About 40 scientists were involved. We work in rota because we have to do many experiments. We have more than 100 investigations. And one key thing is that this was not an engineering testing. It was having a physics experiment in a lab, where the lab is 1 million kilometers about away, and you cannot go there and do things. So we have to prepare, to be very prepared. The time were very strict. You get the data, then you have to analyze them, get some conclusion, and then if you want to do another experiment, it will take 3 days because you have to be sure, of course, first, discuss if it's okay, simulate on your computer, then the SOC, the Science Operations Center, has to simulate the thing, the Mission Operations Center has to simulate, because you don't want to send telecommands that then switched off the spacecraft. It happened already. I mean, if you make the wrong telecommands, it's a mess. So you have to be very well prepared about this. And so we have a number, of course, not everything went okay. So we put many Tiger teams on the single thing. Calibration team, Delta G Night, I was part of this. I was of the Delta G. I was proud. Oh no, the Delta G is gone. But the sugar not. You need it because, of course, it's a stressful environment. We have several yaks in the room to be shared. Many things, many young scientists have to. And this you can see one overseeing the operations. It was fun time. It was funny. So, okay, let's go to the result. Day 0, we have amplitude, spectral density, and accessory noise, frequency. We have the LISA requirement. We have the LISA Pathfinder requirement relaxed by 1 order of magnitude. And we have some prediction. We spent many years trying to understand what could be the dominant noise. And we have a huge document about that. At the end, you can see we are dominated by 2 noise: the actuation noise, the noise that comes because you are applying some electrostatic force to the electrodes, to the test mass, and the Brownian noise, that one then is due to the surrounding gas. And we have this prediction for that. And then the first day, we switched on the system, and bam, we were exactly where we were expecting. This was very nice to see. Well, not exactly. Here we were much, much better because the interferometer guys did such a wonderful job. And the system behaved much, much better than what was testable on ground. We were limited by that thing. So after 1 year, we already reached the LISA requirement. You may have seen this many times in publication, not exactly this data, but something similar. It was not easy. The real curve looks like this one, the blue one, and then the red one. And we have to do a couple of things, more than a couple of things, to reach the yellow one. So first of all, I told you the most dominant thing is the actuation noise. Why this went down? This went down because the main thing why you have actuation noise, because you have to compensate for the force that pull your test bed away. And this is dominated by the gravitational quasi-static field. Now, you can say, yeah, let's build a system that produces 0 force on the test mass. And we try to do this. But to do this, you have to measure every bolt, every screw, everything, know exactly the position. And this, we want, like, at the end, we end up with hundreds of picometer per second square of residual acceleration on the test mass, putting a balanced mass to compensate for everything. Then we went to measure it, and it was 20 picometer per second square. At that point, because the force that you apply depends on the maximum force, then I don't want to go into that because it's a little bit too technical, but it depends directly on that. because we can set the maximum force one order of magnitude less, we went to this level, okay, for the actuation noise. This was a wonderful job from the industry that designed such a gravitational residual field very well. Then we saw this, and this was just because the interferometer was such a good interferometer that you can pick up all the spacecraft motion. But anyway, in any case, we have a model for that. We can model and subtract, and we get here at high frequency the yellow one. The Brownian noise went down because we were pumping out to the outer space. That it worked. The gas was going outside. And then we have a couple other things. The centrifugal force and the Euler force, they were due to the fact that the platform, the spacecraft, was not an inertial frame, was rotating with an angular velocity and an angular acceleration. This will couple with any misalignment of the optical system, giving you this effect. And you have to, however, we were able to do experiment to calibrate this and subtract, and we get this. This was not the end of the story, because we, as you may have heard, we have glitches, these quasi-impulsive force. They can last from seconds to hours and have amplitude of picometer per second square, of tens of picometer per second square. Anyway, we were able to get, to get some phenomenological model for that and to subtract to reach this level. Still, this is something that we are looking for, because we don't have a smoking gun for the effect. We have ideas, very likely outburst or gas of 10 to the 8, 10 to the 10 molecules. But it's something that we have to understand. Okay, so the other thing that we did many experiments, I told you, because we want to pin down the model that build up the measurement noise. And we were very good at that, from 1 Hz to about 0.5 millihertz. Below that, we reach we cannot explain about the 50% in power. This is the bad part of the legacy for LISA, I think. We demonstrate the requirement, but we have a known thing, and we have to keep very well under control. Okay, so I want to just show a picture of the great team behind all this. It's not all the team, in the sense that many people, of course, were involved in the year, and then they changed their job. I mean, but this is a very representative sample. Now, going quickly to LISA, I think, I cannot swear, but I think a project manager of LISA say this, compared to LISA Pathfinder was a toy. I think I agree with that. Because, yeah, LISA will be designed to maximize LPF legacy. Practically, the full acceleration noise budget for LISA is built upon LISA Pathfinder results. But not all the budget. We have new thing. So we will try, of course, to keep all the legacy about environmental cleanness, thermal stability, gravitational balance from LISA Pathfinder. These are the good things. We learn how to do experiment to characterize the noise on orbits. This was not for granted before LISA Pathfinder. We now know how to manage a drag-free spacecraft, and this can be important for LISA. However, LISA is still a new and complicated system with respect to LISA Pathfinder, with a new spacecraft and moving parts. So these are new things. This cannot be proven by LISA Pathfinder. I mean, the spacecraft is different. We have heard, I think from Rita the first day, that you cannot consider the payload separate from the spacecraft. The performance are guaranteed by a combination, an interplay of the payload and the spacecraft. So having a new spacecraft and then moving parts complicates the thing. And this means also that not all is under one subsystem control. It's true that GRS proved the level of acceleration, but now that is in another spacecraft, it cannot alone prove that. We have unknown noise, and we have glitch events. We have to stick as much as possible to LISA Pathfinder legacy, because when you have unknown noise and you don't have control of that, if you make a little change, that unknown noise could become a factor 3 what you have in LISA Pathfinder, and then it affects all the noise. So we have to be careful about that. Not all can be proven and fully verified on ground. So I think we are doing a good job, but I want just to say, yes, celebrate LISA Pathfinder, but be careful that there's a lot of work to do yet. Now, concluding remarks. So LISA Pathfinder was a great success, was made of exceptional hardware, very well prepared data analysis, and a great team running and analyzing many complex experiments in flight in a limited amount of time. We learned to manage and operate these physical experiments in a lab in a space, and I think it will be important also for LISA, at least at the beginning, because I think all the things that we have heard, also the tilt-to-length experiment that Jean-Baptiste talked about before, this cannot be done without going through L2, I think, not L1. You have to go through the global fit to get this parameter, because are small things that affect the noise, but you cannot see if not through TTI and then fit into. So it could be that it should go in the full model for the fit. So the project has been an amazing throughput for being a technological mission at the end. We have more than 40 papers and a lot of dissertation. We have an entire conference in Barcelona last year. I didn't mention that we have also other papers that are not exactly related to gravitational waves, limits on dark matter, collapse wave function model. I mean, many interesting with the data of LISA Pathfinder. And then must be mentioned that several young scientists that grew up in this project then now are having a leading position in LISA. I think it's important to mention. So on a personal account, being part of that, of course, has been an amazing and professional live work experience. And finally, of course, remembering the old days of being a Delta G Knights, I can only conclude like this: happy anniversary, LISA Pathfinder, and may the force be with you, but below 3 in 10 to minus 15 meters per second square. Thanks.
Great. We have time for a couple of questions.
Yeah, LISA Pathfinder is done. No question, right?
Eleonora.
Hi, Daniele.
Hey.
What was the most frightening moment for you during Pathfinder operations? Because I remember what was the most frightening for me, but I'm curious about yours.
You mean the hard time?
Yeah, the time during the mission when you were like, we're screwed.
We were screwed. When the test mass blocked, that was very bad. But personally, there was at the beginning these things that I didn't go to the detail, but we have to calibrate this measurement of delta G. And when we start to do this experiment in which we stimulate the system, and then by fitting to a model, we get the parameters to get delta G, we get something very strange. We get the gain of the electronic that was going crazy. And it doesn't make any sense, and it screw all the measurement that you are going to do. So figuring out that, at the end we did it, we discovered, maybe I think Luigi talked about that, this little error in the digitization of the electronic, a very small thing, a very thing from a lab of electronic engineer. However, the mission depends some way, the result depends some way on that, because they were higher level. So facing that at the beginning of the mission, that maybe was a moment in which, yeah, for you was the glitch first. No. No, maybe.
Question? Ariana?
Thanks, Daniele. This was amazing. So talking to you and also looking at wonderful posters on LISA Pathfinder, I understood better this week that there were lots of experiments happening on LPF, not just sort of things that go beyond also the LPF targets, but also a lot of things to really characterize what's going on there. And I was wondering whether we expect something similar to go on in LISA, or is that all over and we know exactly? Experiment,
you mean?
Yes.
Yeah, I mean, it will depend. We will try to reach the requirements, at least I can speak for the acceleration noise, in such a way that we don't need real experiment outside the commissioning. However, we will need to measure discharge, and if the baseline, that is this continuous discharge, doesn't work, you will have to discharge the test masses, for example. So it could be that you have to do something. If we have this stiffness, the gradient that coupled to the jitter of the test mass should be below the requirement, but if it's not, you have to do experiment to calibrate that to subtract for the data before you can look at it. So we want for the scientists to have the cleanest and the fastest data available for get the supermassive black holes. But it's a complicated thing, and we have to see what we get in commissioning. I mean, but we will be prepared to support you. Yeah. Thanks.
Thank you, Daniele. All right, we're going to continue the Italian theme for this. So far, all the speakers and all the questions have been from Italians. We should just switch languages. But the next Italian up is Emanuele Berti. What's he talking about? Tests of fundamental physics with LISA.
Okay, can you hear me? Is the mic working? All right, so first of all, I would like to thank you for the invitation to give this talk. I had to say that I'm here representing the whole fundamental physics working group, and I would like to start by thanking, in particular, Richard Brito and Lorena Magagna-Sertuce, because they helped me out to collect ideas about all of the activities that are going on within the group. So I would also like to thank the organizers. I think this was not an easy conference to organize. I was looking at this photo, and I think looks like a space nerd cult. When I was looking at this thing, I also thought about something else that I wanted to put right after this slide, but I didn't do it. Remind me at the end, there's another space nerd cult that some of you in this audience may know about, but it's kind of an obscure joke, and I don't know if you'll get it, so I'll put it on only at the very end. It's for real, space nerd. Okay, you'll see. Anyway, so what am I going to talk about today? I will talk about tests of general relativity, and most of the time I'll be talking about systems like the one that you see here. I don't think it needs any introduction. This is 250114, which is a twin of the first system that we observed now about 10 years ago, except that we saw it with much higher signal-to-noise ratio. And this system was widely advertised as providing tests of the Hawking area theorem. To me, personally, this is a system that provided the best tests of black hole spectroscopy, which is something that I will discuss later on. And that's actually a better test of general relativity than just the Hawking area theorem. But I know you know many things about this system. The key thing is that LIGO didn't just do tests on that one system. And now I'm going to spend a little time on this slide. I apologize. I introduced in a single slide a number of acronyms that probably defeats the purpose of the LISA acronym dictionary. But let me explain very briefly what the LIGO collaboration is doing now in terms of tests of general relativity. And I wanted to put this on at the very beginning, not to scare you, but to say that there is a whole series of things that can be tested. LIGO is doing it routinely. And so the way I decided to organize this talk is by explaining what the LISA community is doing that is similar and what it can do that is better than what the LIGO Virgo Kagra collaboration is doing already. So the table that you see here is a giant table that shows the content of 3 papers. Now there are so many tests of GR that the LIGO collaboration splits them in 3 papers. The first paper talks about general tests. In particular, the first is a test by our esteemed session chair, which consists of the simplest thing that you can think of. You fit the data with a general relativity template, you subtract it, and you ask whether what you get when you subtract the signal is consistent with noise. So that's the most basic way that you can test general relativity. The second test is called an in-spiral merger ring down consistency test, where you basically take only the in-spiral part of the signal. You use fitting formulas to predict what comes out after the 2 black holes merge according to general relativity, and then you check that this is actually what you see. The third test is one that says, okay, we know that this waveform should contain several different multiples. With each of the events, I can check whether, given the detection, the relative amplitude of the other multiples is consistent with GR. The fourth test is about polarization. Basically, what it does is It uses the prediction of GR for the polarization you should see in the different detectors to construct something that should be 0 in GR, and it checks whether that something is actually 0. None of those tests are currently implemented, or there's no pipeline to implement them in LISA as far as I know. So what I will discuss mostly is the content of paper 2 and paper 3. Paper 2, as you see, has a battery of different tests. The first are called parameterized tests using mostly the in-spiral. They go under different names. Flexible theory independent, TIGER. PCA stands for principal component analysis. These are all different. I will explain later what I mean because this will be a good part of my talk. Then there are tests that concern the spin-induced quadrupole moment. There is nothing similar in LISA, so you'll never hear it again in this talk. And then there are other tests that are kind of more fringe, if you like. One is not really a test of GR. It checks whether your binary has a line of sight acceleration, maybe because it's orbiting something else. There is a test on dispersion relation that has a special case tests whether the graviton has a mass. And then there is a test on anisotropic birefringent propagation, which basically tests whether gravitational waves propagate as they should in GR. Last, paper 3 of the series concerns the merger ring down, and it has different components. One uses only the ring down, as I will explain later. One carries out an agnostic test based on effective one-body. And then there are other things that I will not really discuss that test for things like echoes in the signal if you don't have a horizon. Now, what's the structure of things for LISA now? It used to be that there was a science investigation work package dedicated to fundamental physics before the reorganization of the consortium. That group put together a review, a living review that should be updated over time. And now most of the activities are organized by the fundamental physics working group. And here goes finally what I will talk about here. Now, what you see, first of all, I will not talk about tests of general relativity with matter because that's what Francisco discussed on Tuesday, and so I won't even get close to those things. The LIGO collaboration, as I said, carried out tests on the loudest events, about 91. There are 91, but they only took the 42 most confident events in O4A. And what you see here is my attempt to summarize all of the things that I told you when I was looking at that table. The stuff that I will actually discuss today is the stuff in red. So I'll talk about modification of post-Newtonian parameters, because these are tests that are being actively implemented in LISA data analysis. And then I will talk about ring-down tests and the in-spiral merger ring-down tests with effective one-body. And finally, because I didn't have enough material, I will also talk about 2 new tests that are being proposed and sometimes implemented in LISA. One consists of looking at the so-called gray body factors. I will explain what they are for people who don't live and breathe black hole perturbation theory, and a test that is based on the so-called memory effect. All right, so let me start. FTIPP, what is the idea here? The idea is that if you take the gravitational waveform in the frequency domain, the gravitational waveform can be expressed as an amplitude and a phase. The phase in the frequency domain can be expanded in a post-Newtonian series in terms of the velocity of the binary divided by the speed of light. So what you see over here, this monster, is the prediction of general relativity for this stationary phase approximation phase. And you see that there are power law terms and there are log terms. Each of these terms is a number once you have measured the properties of the binary, at least if your binary is spin aligned. I don't want to make it too complicated. So what happens is that these numbers psi are predicted once and for all by general relativity. What you can ask is, what if GR is not the correct theory of gravity? Then each of those phase terms here would be modified by some correction. And the way the LIGO collaboration does this This is technical. It splits the part of those terms that doesn't depend on the spins and the part that depends on the spins, and they only modify the part that doesn't depend on the spins. That's because if you include spins, those terms can become 0, and then things can go bad mathematically when you compute Fisher matrices and stuff like that. Okay. So then what do? They show the upper bound on the delta psi term that corresponds to each of those post-Newtonian modifications to the phasing. And the most interesting one is probably this guy over here that corresponds to the dipole term. There are many modified theories of gravity in which you had dipolar radiation, for example, scalar tensor theories. And once you put a bound on this term, you can constrain very severely those theories. So you see many, many symbols here. The ones that matter are the blue and red field symbols, because they correspond to the combined bound that you get from all of the events in the latest LIGO catalog. And then if you look, there are horizontal lines out of all of the bounds that come from the individual events that have been marked in color, because those are the single best bounds, and they come from things like the binary neutron star, which gives you the best bound for the dipolar term. They come from this guy. One of the key skills that you must have in gravitational waves now is remember phone numbers. So that phone number is the lower mass gap event, okay? And then there are other bounds that come from very low mass binary black holes and stuff like that. Now, it doesn't matter. Each of these systems gives you a very good bound, and the question is how much better can LISA do? So that's what many people in the LISA fundamental physics working group are working on. In particular, this is an activity that is led by Emanuele Berti. This plot is from his paper. It's exactly the same thing. And what you see is that we don't know the population, of course, so we cannot do hierarchical bounds, but we can take selected binaries, like the ones that you see here, with certain total masses and certain SNRs. And if you need to remember one thing, the one thing that you need to remember is that LISA can improve by about 2 orders of magnitude with respect to the bounds that the LIGO collaboration is already setting by using binaries on Earth. All right. Next, why is this important? This is important because, in principle, once you set a bound on one of these post-Newtonian modification parameters, you can map it to specific theories that are not general relativity. And this is a table from a paper that I co-authored with Nico Younes and Scott Perkins. You don't need to know what all those theories are. It would take me too far. But the key idea is that if that delta psi is non-zero, then we have a way of mapping it to a specific theory at each post-Newtonian order. The problem with doing this is that we need to understand general relativity better than we do. And so here, I want to advertise a paper that we wrote with Rohit Chandramouli and 2 papers by Sophia, who's sitting back there, that talk about how badly we actually know GR. In fact, what is going on is that there are already events in the LIGO collaboration that show you apparent violations of GR because of missing physics. If you don't include eccentricity or precession, you may think that you have a violation of GR when in fact you have not included enough physics within GR. And these effects are expected to dominate more and more for next generation detectors on Earth, Cosmic Explorer and Einstein Telescope, and things will only get worse for LISA. So maybe this is not the fanciest job if you want to be a theoretical physicist, but it's one of the most important things that we need to do in preparation for LISA. And what is going on within the community now is the implementation of these FTI methods in LISA tools by Emanuele, and the implementation of a slightly different flavor of these tests that uses what is called parametrized spinning, effective one body, NR. You don't want to know. But it's a different way of doing parametrized tests using the full spiral merger ring down, and that's happening. What is not happening is what you see down here. So we want you. If there are people who are interested in doing things like implementing Tiger, looking at the effects of waveform modeling, including additional physical effects, doing injections beyond GR, you are all very welcome to join the gang, okay? I'll go back for Arianna. Okay, you can take the photo. Okay, so good. Now, next. Next, I'm going to talk about linear and nonlinear black hole spectroscopy. If you remember, there's a paper 2 in LIGO and a paper 3. So now I'm going to focus on what would be paper 3 in LIGO. This is for people who don't do black hole perturbation theory all the time, my one-slide summary of what you really need to know about black hole perturbation theory to understand what I'm going to say next. So imagine that you take a black hole and you perturb it by scattering either a scalar field or an electromagnetic field or a gravitational field, okay? You can do a lot of math, and what you discover at the end of the math is that if you work in the frequency domain and you separate out the angular dependence, everything reduces to a scattering problem with a one-dimensional radial potential barrier. So that potential barrier is pretty simple in GR. Ignore this bump. It just goes to 0 at the horizon of the black hole, and it goes to 0 at infinity. So now imagine that you take some wave of amplitude A ingoing at infinity, and you throw it in. Some of that wave will go through the potential barrier, and some will be scattered out with some amplitude that we call A outgoing, okay? How much of that wave goes in and how much goes out, you can determine by doing things that you learned in quantum mechanics, non-relativistic quantum mechanics, okay? So there are some proper oscillation modes of the black hole that correspond to setting this ingoing amplitude equal to 0. Because then what's going to happen is that over here you only have waves going in, because it's a black hole, nothing can come out classically, and you have no waves coming in from infinity. So that corresponds to not stimulating the emission of the black hole. Those are free oscillation modes of the black hole in that sense. And when you have a differential equation like this and you impose 2 boundary conditions, no outgoing waves here, no incoming waves here, you can solve for the whole spectrum, and you discover that there is a spectrum of discrete frequencies that you can compute. The second thing that is important in this scattering game is the so-called reflectivity. It's basically the amplitude of the outgoing waves given some incoming wave amplitude. This reflectivity is important, and it's related to something called the gray body factor. Why is it called the gray body factor? Because you probably heard that, according to Stephen Hawking, black holes radiate at the horizon like a black body. But what you observe is actually not a black body spectrum, because some of the Hawking radiation emitted here has to go through the potential barrier. So this reflection coefficient is related to how the black body actually looks gray when you look at it from infinity. Okay, that's the idea. And I will go back to this gray body factor later. It's a property that you can compute once and for all if I give you a black hole with a certain mass and spin. Okay, so the spectrum of black holes looks like this. I don't have time to go through the details, but basically it's usually dominated by this mode down here for a non-rotating black hole, because that mode has the smallest imaginary part. The imaginary part is the inverse of the damping time of the oscillation. And so small imaginary part means that the mode lives for a long time, and I expect to see it in the signal emitted by a binary black hole merger. If the black hole is rotating, then there is a splitting, like when you do quantum mechanics and you introduce an external electric field in a hydrogen atom. And what happens is that this splitting depends on the magnitude of the spin of the black hole. So, long story short, if I measure some real oscillation frequency and the imaginary part of the oscillation frequency, I can determine the mass and the spin. And then if I have any other measurement of another frequency and damping time, I have a test of general relativity. And I can do something like what people here do for binary pulsars. I can combine all of these observables, and then I'm going to get different strips in the real imaginary part or in the spin mass plane. And if general relativity is correct, all of these strips that correspond to measurement errors have to combine at a single point. So this is the consistency test that we want to do. To do it, we need to detect at least 2 modes, but the more the better. If we have many quantities that we can measure, we can make many tests, and they all should match at the star. That's the idea. Now, what is the difficulty in doing this? That we don't know exactly when this ring down starts, because at the beginning you have a very complicated system. This is taken from SXS simulations, where the 2 black hole horizons have not even merged, so you don't have a single black hole. And then at some point, you will have, at the peak of the radiation, that maybe you are close to forming a common apparent horizon, but perturbation theory is only going to be good when you go late enough after the merger, because then you really will have a small deformation of the final black hole. And so if you want to perform a fit in terms of quasi-normal modes, you'd better wait. You should wait, and the later you go, the better your test of general relativity using ring down is going to be. The problem with this is that the later you go, the lower the signal-to-noise ratio. So there is a compromise. And this caused a lot of controversy in the past few years that I wish I had never gotten into. But there were lots of claims that we had already done these tests with the very first event. I didn't quite believe it. We spent a lot of time arguing. Long story short, if you want to read about it, there's a 300-page review that tells you everything you ever wanted to know, and maybe even more. This beautiful illustration is by Anna Carvalho, and this thing has been published, and I don't want to see it anymore. But if you look at this plot, it shows you that the results that you get on that first event really depend on the modeling assumptions that you make. Where do you start? Okay. Where do you start? And lots of other things that I don't have time to get into. So there's going to be another workshop on this. You see, this is the bridge in Lisbon, for those of you who have been there, superposed with a ring-down wave. And there's going to be another meeting in this. This is a very active area. There's going to be a meeting on this every 2 years, and this is just the next one. Okay. What are people doing in terms of these ring-down tests? Simon Menot is implementing the tool that is currently used in LIGO for LISA. And this is not an easy task because it's a time domain code, but when you do the time domain analysis, what you need to do is make sure that you take into account the fact that the LISA response is, as you all know here, dominated by TDIs, and the ring down can last -2 hours for the massive black holes that we want to see with LISA. So recombining the observables in the right way is crucial, and that's exactly what's happening here. There is a whole tutorial, if you are interested in joining the Army, at this URL on how to use PyRing for LISA. And there are several side projects that I will not have time to discuss that look for things like charge on black holes, or modifications of beyond GR theories to these black holes. And again, I wouldn't have time to talk about it in detail, but you can ask me later. One thing that I want to mention is that one of the most exciting possibilities allowed by LISA is to measure nonlinear quasi-normal modes. This is something that goes back in time to when numerical relativity wasn't working and people were trying to develop second-order perturbation theory to resurrect the numerical relativity simulations that were dying, hence the Lazarus figure here. But what used to be a way of fixing numerical relativity that doesn't fit now, that doesn't work, became now a way to analyze numerical relativity simulations to understand their nonlinear mode content. And the very brief message that I want to tell you is that next generation detectors on Earth may see a handful of these quadratic quasi-normal modes in binary mergers, but depending on the populations that we don't know, LISA could see up to thousands of these. Of course, everything depends on astrophysics that we don't understand enough, but that's the message. I also, and this is from a paper by Sofia that you can see there. I want to talk about two more things if I have enough time. One is this business of the gray body factors. The idea here is that I told you that the gray body factors basically measure the transparency of the potential barrier around a black hole as a function of frequency. And there are numbers that I can compute once and for all. Now, the amplitude of a gravitational wave is basically the square root of the energy that is contained in the gravitational radiation. So there was a paper by Okabayashi and Oshita where they said, if I take the Fourier transform of the in spiral merger ring down signal and I look only at the last part, I can probably fit it quite well by just taking the square root of this reflectivity number that I was talking about before. And they proved in that paper that you can get, just by doing that, you take a constant amplitude and you multiply it by the square root of the reflectivity. In the frequency domain, that gives you a mismatch that is of order 10⁻². Then we said, okay, maybe you can do even better because there could be corrections. Let's say that they go like a power law of the frequency. And we found that by just adding these two parameters, A and P, instead of a single parameter A, to the fit, you can bring down the mismatch in the frequency domain by another 2 orders of magnitude when you fit the amplitude of the gravitational waves. Then we saw that this can be, okay, I don't have time to go into the details. You can ask me later. You can add the phase to the model, and you find that the fit gets even better. And then what we proposed to do was, instead of having to deal with all of these ambiguities on when the ring down starts, you can just try to take the last part of the waveform in the frequency domain, so the high frequency part, use these gray body factor, simple gray body factor models, and try to infer the mass and the spin in that way. And what we find is that it gives better results than what you get by ring-down models. So I think this is something that we should exploit in LISA. In fact, I have preliminary results that show you that if you do this for LISA, you can reduce, you can get the masses to a part in 10 to the 4, the spins to 1 part in 10 to the 3. It's amazing, okay? The very last thing that I want to mention only in passing is that there is an effort to detect gravitational memory. I will not say much about this, but Jan also gave a talk in one of the parallel sessions. If you want to hear more, you can ask me in the Q&A session. Basically, LISA has very good chances of detecting memory effects, and this is important because it's something that people in the string theory community care about very much for reasons that you probably don't want to know about. So, conclusions. These are all the tests that have been done in LIGO. The ones in red are things that have already been done in LISA or are being worked on. And there are many things that have not been implemented. If you want to work on those things, you can talk with me and I can put you in touch with people who are actively developing these pipelines. Thanks.
All right, we have some time for questions. Colin, I think, was first up over there.
Thank you. Nice summary. I was just curious about the constraints on the PN coefficients that you showed. I think the current LIGO analyses, when they do those, they can only vary one coefficient at a time. Is that right?
Yeah.
With LISA, will we be able to vary all of them, or are those constraints that you're reporting there still only varying one at a time?
The very good point, Colin. So this is a major. I agree with you that this is not what we should be doing. So the answer is what is being done now is exactly the same thing that is being done by the LBK. So one at a time. We could and should do better than that. With LISA, presumably, if we have very loud events, we can do a little better. In defense of doing things this way, I am not a fan. I have several problems with this. But in defense of this particular way of doing things, there was a paper by Nico Younes and friends where they took a specific theory in which you know what the next to leading order corrections are. And what they showed in that paper is that if you include the leading order term and the next to leading order term, and you do tests in this way, the bounds that you get are actually better than what you get by including only the leading order term. If you want, we can discuss it later.
Okay, thank you.
All right, the next hand I saw was Shane. I think that might have to be the last question given time.
Okay, thanks, Emanuele. So this is all what I would call strong field tests of GR. One of the advantages we have with LISA is we'll have multi-messenger sources. So can you comment, because I know you didn't talk about it, about the opportunities for propagation tests, testing, the null travel, biometric theories, all of that sort of stuff?
So I can, and if you had asked me the same question before GW17 or 817, I would have said we can do amazing things, but they have been done. And so I find it very unlikely that we will be able to do much better in terms of propagation properties than what we have already done with GW17 or 817. It's possible, but unlikely.
All right, well, thank you, Emanuele. What was your joke?
Oh. The important stuff. Let me go all the way to. So I was saying that we look like a bunch of space nerds, and then I'm like, I think I've seen this before. And I had seen it before. Now, most of you won't understand it. Do you know who they are? Okay. So this is a microtonal progressive rock band from Canada. I told you it would be obscure. But you should look them up. They are called angine de poitrine, which means something like heart attack. Anyway.
All right, thank you, Emanuele.
Like this. Okay.
All right, next up we've got Antoni. I'll let you take it away. I'm going to tell you at 20 minutes.
Yeah, it's short.
I'll give you the 5 thing.
Yeah, it's perfect. Okay. Yeah, today I'm going to talk about a bit what we are doing regarding one of the main sources that we will be detecting in LISA, that they are massive black hole binary waveforms. And in particular, I will talk about the work that we have been doing in the massive black hole binary subunit within the DDPC, and with a particular focus on one of the ongoing mock data challenges for LISA, that is the Mojito, that, as you have heard, is heavy and light, so I will go a bit into what that means. Let's start a bit by the beginning. So what is the DDPC? And of course, I am not LISA science team or anyone above that, so I defer to people higher up to explain this more faithfully. But just a brief overview of how everything is structured. So you have, on top of everything, there is this MLA, that these are the multilateral agreements between countries, where countries are committed to deliver certain parts of LISA. In the sense, when I will just focus on the analysis, the science, and then there is, in LISA, there is the PO and the SOC and the LST, the LISA science team, which are the main managing entities. And then below that, there is the DDPC, which is the block that you can see down. That is essentially the project office that is managing the DDPC. And this is now subdivided into the system team and the science experts, that are the ones that trigger decisions that need to be made, like if, for instance, a certain mock data challenge needs to be postponed by a certain, by not meeting certain deadlines, or something like this. And then there is like a bunch of acronyms that you don't need to know now, but I will try to explain to you. The first one is something called L01, which is, for instance, led by Jean-Baptiste, that gave a very nice talk about TDI today. They are in charge of taking the data from the spacecraft and processing the data. Then the next one is called L2A, but in practice you can forget about this and just think about the low latency coordination unit, that they worked essentially on doing follow-ups of the events, on trying to search for the most bright events in LISA. These are the massive black hole binaries. Then there is the so-called L2D. These are the people developing the global FIP pipelines. And essentially now in L2D, there are 2 official pipelines in the DDPC. They are Erebor, developed mostly at DAI by Alessandro Santini and Jonathan Gere and other people, and also Michael Katz. And then there is also GMU, that is mostly APC, that is developing these 2 different pipelines. Then there is L3C, that is, for instance, is led by Ariana, Astrid Lambers, and other people that are this group in charge of doing the catalogs. So once we have produced these very nice posteriors with L2D, that they have to solve this issue that they have with the global fit, then they will be in charge of producing a catalog and providing it to the community. And finally, well, there are 2 sub-blocks. One is the CUSIM, where we had a very nice talk by Jonathan Menu this week, where he explained in detail the content of the Mojito mock data challenge. They are in charge of producing the so-called bricks, that are the blocks containing the different sources. In this case, for the Mojito data challenge, what we are doing is we have bricks for each source, as he explained very nicely this week. And finally, what we have is CUWAF, that we produce waveforms for the different sources. And now I will go a bit into detail into what this CUWAF means. So this is a bit the overview of the DPC. So what is the coordination unit waveforms? So this was formed in 2024 and is in charge of providing the waveforms, the waveform infrastructure for LISA. And as I said, there are these multilateral agreements in which the countries commit to do something. In this case, the two countries that committed to the waveforms were Germany and the UK, but as of course this is a very dynamical situation. Now, for instance, Spain may join soon too, because we are also actually working heavily on waveforms. And here I just put some names of what are the current chairs and how this subunit is working. So this is divided essentially in sources, and each source we have a number of experts that contain the developers and also people who want to contribute. And essentially we have massive black hole binaries that I will focus on, but then we have also the stream mass ratio in spirals, the stellar origin black hole binaries, that these are the binaries that we will observe in the LBK, that we are observing in the LBK, that they are just in spiraling during the LISA frequency band. Then we have the galactic binaries, cosmological sources, and also cosmic strings and bursts. And for each of them you have, I just mentioned the chairs, but beyond the chairs there are also working groups of people, early career researchers, and also senior ones working towards implementing these waveforms in the DPC and the ESA infrastructure. So what is the massive black hole binary subunit? Essentially we are mostly having members from two different institutions that are in Germany and Spain, and they are mostly PhDs and postdocs, but also we have contributions from the UK to the subgroup. One of the main principal activities, and this is what I will talk in depth in the next slides, is the development of waveforms for mock data challenges. And in particular for Mojito, and I will go into detail, develop a waveform generator that is not just for massive black hole binaries, but also includes other sources, and also contributes to the conventions of the missions that I will talk a bit later. So let's just start from the beginning. So we have heard that there are these different LISA common data sets that for some reason have been named by alcoholic drinks. I don't know why, but apparently the current one that we have is Mojito. And if you increase the alcohol and combinations of several alcoholic substances, then you can increase in the number of schools that you have here. And then the last one should be Aunt Roberta in 2031. But currently we are in Mojito, which is this one, and this is the one that I will try to explain. And I will try to explain what is in it for each source. So massive black hole binaries, so these are, in Mojito Heavy, what we are dealing with are spin precessing quasi-circular binary black holes in quasi-circular orbits. So black holes that orbit each other in a quasi-circular orbit, but they have arbitrary spins in any direction that you may think of. And this imprint that you can see here is the time scale of the spin precession. So that's the wobbling or the orbital plane due to the misalignment of the spins. And here, what I just plotted here is some of the distributions that we have been using for Mojito. This is taken from Hungary, but this is based on some population codes. Essentially, what we have two situations. One is for Mojito Heavy and Light, and as Jonathan described, for Mojito Heavy, we are using, the plan is to produce bricks for 100 sources, while for Mojito Light, that is the testing version of the L2D pipelines, we will only have 20 massive black hole binaries. Which kind of models are we using? We are using IMR phenom TPHM, that's a phenomenological waveform model for in-spiral merger and ring-down binary black holes. And then the SEOBINAR B5 PHM, that is the state-of-the-art effective one-body waveforms for massive black hole binaries. both of models are also used in the LBK analysis. So next one is extreme mass ratio in spirals. Probably I don't have to say much because there have been so many exciting talks about development of extreme mass ratio in spirals that I will not add much. But you can see that what you have is a very massive object, and then you have a small secondary that is orbiting around this supermassive object, and it can have very complicated orbits. In the case of Mojito, we are just restricting to Kerr-eccentric equatorial, and this is just through the few waveforms that we had very nice talks during the symposium by Michael Katz, Niels, and other people regarding few. And in the case of MRIS, for heavy, we have 100 sources that we are planning for, and in the case of light, just 8 sources. Regarding galactic stellar binaries, these are essentially, this could be white dwarf, black hole, or white dwarf neutron star. For these, the plan is to use around 4 million for heavy and 15 million for light, using JAX-GB, that is a JAX version of the galactic binary code. And then no black hole pairs for Mojito. But we plan for white dwarf neutron stars with pi-FP, that is an in-spiral PN-based model. And we plan 42 for heavy. And this, you can see that there has also been many talks about galactic binaries, so I will not. This is just a plot of the TDIX as a function of time, and you can see that as we have so many, they create a background, well, a foreground already. So, and then we have also the extra galactic stellar binaries that we will have black hole in this case, and we will have around 20 with pi EFP and around 6 for Mojito heavy. And again, for the detail, and there are 2 main things that we need to add to Mojito, apart from these sources. One is the stochastic gravitational wave background, and the other is the noise of the detector. Regarding the stochastic gravitational wave background, here we will not, in Mojito Light, nothing was added, but in Mojito Heavy, we plan to add 3 cosmological sources for the stochastic gravitational wave background, and 1 from astrophysics models. And finally, from the instrumental noise, there will be 2 noise data sets, one more simple and one more complex, and with different properties regarding switching on of laser noise, tilt-to-angle couplings, and so on. And I defer to the nice talk by Jonathan Menu with all the details and further details on this kind of sources that will be added to Mojito. So now a bit onto what are the massive black hole binaries that we are going to see in Mojito. Reminder that massive black hole binaries will not last for the for the full stretch of data, but these will be very bright sources that they will be mostly the most brightest signals in LISA. And for this, we use 2 multipolar waveform models. So these include multiples beyond just the leading order quadrupole. And they are just limited to quasi-circular binaries for these mock data challenges, but they include arbitrary spins, because so far the previous data challenges have been using just line spin binaries, which are restricted to the orbital plane, for instance, Sangria. And these are just 2 models with maybe not very commercial names, but essentially the P is for precision and HM for higher modes. And what we have is like we have the phenomenological on one side, that usually they are fast and accurate models within the phenomenological family. Some of them are coded up in large shoot, and they were reviewed by the LBK, but we have also an implementation in Python that is through the PhenomXPy package, and we have reviewed this within the DDPC and massive black hole binaries for Mojito. And then we have also SEO-binar B5 PHM. As I said, this is within the effective one-body formalism, that is an effective description of the 2-body problem, where you have a modified Kerr background, where the modification parameter is the symmetric mass ratio. And then this is coded up in PySEO-binar, which is an existing Python package that is publicly available, the same for PhenomXPy. And there is a new, more efficient implementation for Mojito MDC that hopefully is going to be public quite soon. And here in the plot here, what I am having is just a figure of merit of the accuracy of the models against the data set, the public data set of NR simulations, of the simulating extreme space-times collaboration, of the different phenomenological models. Here the X you can forget, but just focus on the two that we are interested in. And this is a figure of merit that is the mismatch as a function of a certain total mass range. So this plot, I took it from the LBK. That's why the total mass range is not the one that we are used to for massive black hole binaries in LISA. And then what we can see is that these models are relatively accurate for the LBK, but now we want to understand if they are also accurate for the LISA data analysis. So we have to do several things. One is we have reviewed these models within the DDPC, IMR phenom TPHM and B5PHM. We have check conventions. Something that was needed for the Mojito data analysis is the generation of waveforms in a specific time arrays, and this has, for instance, been implemented. There have been comparisons against numerical relativity, profiling, and timing, and here is just a plot showing the conventions that if you adjust for the conventions of LISA that are different from the LBK in terms of, for instance, the line of sight connecting to the two black holes, that this can lead you to a very different parametrization of your source frame. So then you can get very good agreement between the different conventions. And then there are several sub-projects within the massive black hole binaries, so we are not just an homogeneous project that works towards something, but there are several sub-projects. One of them is the development of a mismatch code that is done at the Albert Einstein Institute in Potsdam by Arnab Dani and Gonzalo Morras. So essentially what they are doing here is they are generating the waveforms using the different TDI combinations, second generation TDI, and then developing a figure of merit like the mismatch with the goal that, and this is just work in progress, for instance, here we have the generation of the waveform models with different responses. You can use the LISA GW response, the fast LISA response, that they have different approximations for the response of LISA. The main take-home message is that the goal of this project is to just find the figure of merit that can relate the accuracy of the massive black hole binary model that you are using to the bias that you would get in a global fit pipeline. The next one is the memory usage and profiling of the models. So here we have that the PhenomeXPy model, so that's the phenomenological model, can be generated within CPU and GPUs. As you have probably heard during this week, most of the global fit pipelines, they might need GPU, or they have support for GPU, for batching waveforms and so on. So that's why it's also important that the native source models provide such support, while PySOBNR only has, for the moment, CPU support, but they are working on, for instance, a JAX version of PySOBNR and also JAX version of PhenomeXPy for Mojito Heavy. And here what we show is just a plot of an estimate of the wall time of the different SOB models. And you can see that currently the wall time is not the best for LISA, and we have to work on improving. And then we are liaising also with the global fit pipeline developers like Erebor and GMU on integrating these models and get more accurate likelihood estimates, likelihood cost estimates for these models. And another task that we have been doing is liaising also with CUSIM and validating Mojito Heavy and Mojito Heavy not yet, but Mojito Light datasets. Next one has been the conventions, contribution to the Rosetta Stone document that I think publicly is called the LISA Science Ground Segment document, into which you can find therein all the conventions that currently are describing the different source frames, the different conventions for the waveform generation for the different sources. And we have been contributing to this document that you can also check publicly in arXiv. There is also currently the integration of numerical relativity waveforms and also probably the surrogate models that are finite length signals, which may not cover the full LISA band. So we need to understand how to integrate these models into our pipeline. And finally, what we are also doing is developing new waveform generator for LISA. It's just a Python-based interface that can handle different sources. So far, it's mostly stellar origin black holes, massive black holes, and MRIs, but we hope that we can also include bursts, cosmic strings, and galactic binaries. But there is some work ongoing on developing this within the DPC. And finally, we have also a development plan for our subunit. Essentially, what we want to meet is the timeline of the mock data challenges. So we have a timeline where we have now Mojito Heavy. We need to analyze Mojito Heavy start the analysis by the end of this year. So we need to produce massive black hole binaries waveform models that are efficient and accurate enough for that to meet the requirements of the injection dataset, because the injection dataset has already been produced with this waveform model, so we need to at least be able to produce the same models with computationally efficient enough that they can be run by the global FIP pipelines. So here I'm just listing some of the things that we have been doing so far until 2025, 2026. So these are the things that I have just mentioned now. Some of the things that we need to do is to interface the generator with global FIP pipelines and also low latency, because as I said, for L2A, that were the main source that they are doing low latencies, massive black hole binaries. We need to provide them also with waveforms. This is some ongoing work. We need to develop the infrastructure, so this mismatch project that I just commented on. So we are working on that. And also the next thing that we want to do, once we have done quasi-circular and arbitrary spins, we want to add eccentricity, because we know that eccentricity will be a major effect that we will detect in LISA. So the next thing to do is to review the line spin waveform models with eccentricity. But of course, as we are in a space mission, so things go with delays. So if this happens this year or maybe next year or 2028, we will see. And finally, by 2028, we want to start reviewing models that include both spin precession and eccentricity and provide it to the DPC. And for the future goal, maybe end of this decade, we want to include also the intermediate mass ratio in spirals and also incorporate beyond GR effects and environmental effects. Of course, if time permits, because more data challenges may bring us with new challenges that we cannot imagine right now. And just to conclude, so we just formed in 2024. It's difficult because these are just volunteer people who have volunteered to do work for the LISA DDPC, ground segment of ESA. So the goal of the subunit is to just provide ready-to-use waveforms for the LISA mock data challenges. We are starting with Mojito, where we are just including 2 multipolar quasi-circular precessing spin waveform models. And the main short-term goals is to assist L2D with the analysis of Mojito Heavy, develop a waveform generator that is generic, and the waveform generator can be used by LISA, but also to support 3G detectors like ET and Cosmic Explorer, as well as the LBK, and extend the data set to include eccentric and precessing massive black hole binaries. And that's it. Thank you.
All right, we have some time for questions right here.
So when you say review, what do you mean by that explicitly for the data challenges?
When we say review, is that there is a team of people, including a reviewee, that is the person who mainly has developed the code. That is the person who mostly has set most of the review tests. Then there is a review chair that is external and not connected to the development of the waveform. And there are a set of reviewers that are also not connected with the development of the waveform. And then this team of reviewers plus the reviewee, they meet regularly to check the tests that have been performed, suggest more tests, and then carry forward the review. In terms of review, what you usually test, you test robustness of your waveform model, you test speed, you test memory leaks, you test your quasi-circular limit if you are eccentric, you test your aligned spin limit if you are eccentric, you test comparisons against NR, you test comparisons against other waveform models, you test conventions, you test your CI pipeline. Probably soon there will be also test of the sonar cube, so accuracy of your code, or maybe data quality of your code, because this is imposed by ISA, the use of some of these data quality tools. So there is quite some things that we are doing.
Just going to use chair's prerogative and ask a question. So you've got the SEO BNR, and you've also got the IMR Phenom T family in there. So the data set, are both kind of waveforms being generated, like, or is the data set only one that we get to use?
Yeah, maybe thanks for the question, because I may not be very precise when I said it before. I might have not been very precise, because for Mojito Lite, it's only use a phenomenological waveform model with aligned spins, as you might have heard. That is the Phenom THM.
Yep.
That is coded up by Alessandro Santini at the AI, but it reduces exactly by numerical error to the one that I just posted here in the aligned spin limit. And then your question was whether and then for Mojito Heavy, there are two, there are two data sets that are planned for the massive black hole, because we have two models. One is to produce with SBNR-B5 PHM and with IMR Phenom T PHM some of the sources, and then at least do the analysis with one of them, at least with probably the Phenom is the fastest one, so at least that you have an unbiased wave recovery, and then for the other one, where there can be difference between waveforms, you may have biases that are coming from the waveform systematics.
Right, great. I mean, I can tell you, I've coded up the IMR Phenom T1 for glass, on the NASA side, and we aren't going to be using, I haven't got enough time to wait around for SEO BNR to run. I mean, our analysis would take years if we were using that waveform. We're sub millisecond with the phenoms, but
No, but even with the IMR Phenom T PHM and with the SBNR-B5 PHM, I don't think that currently running the global fit pipelines is feasible, but there are work, hopefully by the end of this year, to provide JAX versions. But when I say provide, it's not just this will be LISA DDPC internal, but we plan to provide it to the community. So if people in NASA are also doing the global fit pipelines, we can, you will be able to use it. Maybe you will have to adapt a bit your waveform generator or what you are using, but the plan is to provide waveforms that can generate in milliseconds. When you talk to Stas, I think he talks about in 20 minutes, you need about 5,000 effective samples or something like this. These numbers we still need to figure out, but we are committed at least to provide waveforms, not just to ISA ground segment, but to the whole community.
Great. Ariana?
Thanks a lot, Tony. I guess I have a bit of a follow-up to what Neil said. And so there isn't just the worry about having waveforms that run efficiently in the global fits, but there's also the fact, and as we heard from Astrid earlier this week, that the catalog is meant to release, let's say, both the best fit parameters, but also waveforms that accompany those, essentially guidelines to the community of what waveforms do these parameters even represent. Where should I be calculating what waveform? And so I'd like, do you think, like realistically, right, that we would be using different waveforms in the searches and then in the release? Or how specific do we need to be when we talk to the community about what waveforms to use with what parameters and where they come from?
I mean, I guess the question is if the searches and I think the goal is that you don't have to think, oh, I am using IMR Phenom T that I coded up in glass or that I coded up in Fentax. So the goal is that there is IMR Phenom T PHM or there is SBNR-B5 PHM, and either it's good enough or maybe then there will be something else, but the goal is to meet the requirements of L2D, that is that they can be run by global fit pipelines, and I think that they are more expensive than the searches, from what I understand. I am not an expert in the L2A, but the goal is to meet that. If we could do it by December or if it will be January, I cannot say, because that's development work that is a bit outside the DDPC, but very connected to the DDPC.
All right, one last question before lunch, right over there.
Hi, thanks for the great talk. I was just wondering, how sensitive is LISA's parameter estimation to imperfections in waveform modeling?
I think that's a golden question. I mean, if what we are going to see is SNRs of thousands, of 100, then might be systematics of waveforms between waveforms, but they might be systematics of effects that the waveforms do not include. For instance, if I don't include certain number of YLM, higher order modes, if I don't include maybe some effects of memory, like oscillatory memory that happens at merger ring-down. So I cannot give you some quantitative statement of how much waveform systematics matters, but from what we have seen, some of the tests of the mismatches, it really matters. Might depend what portion of the massive black hole binary you are seeing, if you are seeing a lot of merger or more in spiral together, but definitely it will be really, really relevant.
All right. Well, thank you very much, Antonio. Antoni. Thank you. And Peter, was there any announcements from the organizers, or we're all good? Okay, lunchtime.